Ham Radio 2.0, episode 66, part 3. This is the third part to the general license class, general license exam class, general license class, put on by the Hurst Amateur Radio Club. Special thanks to Mike, N5YM, and Chris, KD5HIY, for allowing me to record them and record their slideshow and put it up on my video series. I hope I've got a lot of people who have watched my episode 38 and asked, when is the general class coming? When is the general class coming? Because I mentioned it several times in the opening segment of episode 38. Episode 38 is, of course, my new technician class, or my episode of the new technician class. It's not my class, but it's my episode. So this episode 38 is the technician. This is episode 66, which will be the general. So I hope a lot of you get some good information out of these 3 segments and are able to get your license class upgrade. I'm working on one of the clubs locally that does an extra class, so fingers crossed. We just got a new question pool for the extra class in 2016. It just updated in June or July. What is the beginning or the end of June? I forget when it is. It just updated this year, 2016, so they'll be good for another 4 years until 2020. And I'm trying to see if that same club who did extra classes last year with the old question pool, I'm trying to see if they will be putting on another class for extra license class upgrade. And if they do, I've already asked them if I could record it, and they're supposed to be getting back to me. So more to come on that soon. But let's get ready for the third segment of the general license class put on by the Hurst Amateur Radio Club. 73, guys.
Well, good morning. Good morning. And welcome to the third and final session of our general class license training. I'll start off by asking, do y'all, and we talked about one of them already, do y'all have any questions with regards to what we've talked about in sessions 1 and 2? Is there anything you need clarified or need explained? If not, we'll push on to session 3. We stopped the last session with inductors. We talked about inductors and we talked about inductive reactance. And we're going to be talking about capacitors and capacitive reactance now. And we'll first talk about an electrolytic capacitor. If you remember right, a capacitor has 2 plates, 2 opposing plates, and they have some sort of insulating material in between called a dielectric. Okay? And I'll show you a picture, show you some capacitors here. You'll look on here, there's a ceramic disc capacitor right there. The ceramic disc capacitor has a material in between, ceramic material in between, and a metal plate on either side is covered with an insulator. Well, all of a sudden, capacitance is essentially a function of size. How big the 2 plates are, and what kind of material there is in between, what kind of dielectric material there is in between. If you want a really large capacitance, that little disc capacitor will keep going bigger and bigger and bigger until it got the size of a dinner plate or larger, which you don't want to do that. There's another opportunity, and that's called electrolytic capacitor. An electrolytic capacitor is layers of foil. There's layers of foil, and the dielectric material is in between the foil. And the dielectric material is pretty thick. It's kind of a paste, a semi-liquid. But what happens when you apply voltage to it, it creates more of an insulator. It becomes less conductive. So you take these pieces of foil, and it's like you're making a jelly roll, and you spread this dielectric on it, and you put another piece of foil on top of that, which is the other half, and you spread some more dielectric, and you put another piece of foil on top of this, and this piece of foil may be 5 or 6 feet long. And then what happens with that is then you alternately interconnect each of those layers of foil together, and come out with a lead, and you roll it up like a jelly roll into a compact package and put it in a container. There's a small one right there on there that shows 2 leads coming out the end, on a capacitor up on the top there. Yeah, and there's also larger ones. Here's a larger one. That's one in a can. That's about, I don't know, that's a couple thousand volt capacitor on that. So what it amounts to is you save space by making these electrolytic capacitors. But the fact that you have to put voltage on them means that they're polarized. They have a plus lead and a minus lead on them. So the negative and positive terminals are leads, and you got to connect them correctly to cause that material, that dielectric in the middle, to reach its proper conductance or insulating capacity. And if you don't, I built a power supply one time, and I put it together, and I turned it on, and I heard this explosion. It bounced up off the table, and I had the dielectric capacitor connected backwards. And what it did, it just blew up. Good thing it was all right. A good thing, I usually test stuff before I put it in the cabinet, put it in the enclosure, and I thought, go ahead and put it together. I feel good about this. I'm glad I did, that way it didn't blow up all over the place and over me. But it has a very high ratio. The thing about electrolytic capacitors, they have a very high ratio of size to capacity value. Dielectric, does this make sense?
Yeah.
Okay. Hopefully the picture looks good. We looked at some ceramic capacitors. We talked about ceramic capacitors. There's one of them on there. They're pretty simple. They're just a simple little piece of ceramic material. They have a metallic coating on either side, which makes the plates. The ceramic is the dielectric insulator. And they're cheap. They're low cost. They're not polarized. You don't have to worry about those. Though the problem with those is they're really not very stable. With changes in temperature, they tend to change value. So as your radio warms up, they'll change value. And a lot of the old tube type radios, and the old tube radios where there was tubes inside where it generated heat, what you do is you turn your radio on, and if you try to use it right away, it would drift. The receiver would drift, or the transmitter would drift. It would drift because as the interior of the case was heating up, the components like the ceramic disc capacitors were changing value slightly. And it was changing the characteristics of the circuit. So you turn, if you had an old tube radio, you'd either leave them on all the time, but more likely than that, you turn them on about 30 minutes before you wanted to use them and let them warm up and stabilize. Transistorized material, transistorized equipment, and equipment with integrated circuits still has a little bit of drift, not as much. But a lot of what you use is polyester capacitors. They cost more, but the advantage is they have better temperature stability and a higher value of tolerance. On the disc capacitors, they're marked with the value and then a plus or minus tolerance. And that tolerance, you take 2 or 3 of them that are marked with the same value and measure them, and you might not find that they're all the same. How much variation's in there depends on the tolerance of the capacitor. The polyester capacitors don't have as much variability in them. And, you know, in a lot of circuits, there was something else in the circuit that you could adjust to compensate for that. Or you selected better capacitors when you put it in your circuit. Capacitance is measured in farads. That's the value of capacitance. It's measured in farads. Now let's talk about reactance. Okay. On a capacitor, the reactance, which is the opposition to the current flow in that capacitor, based on frequency. At a low frequency, the capacitor reactance increases as frequency decreases. So the current flow is pretty low. At a low frequency, you don't get much current flow through that capacitor. However, as you increase the frequency, the current flow goes up, so more current flow goes up. So the reactance in a capacitor decreases as frequency increases. The higher the frequency it goes, the less opposition there is. If you remember on inductors, it was just the opposite. In inductors, the frequency decreased. The reactance increased as the frequency increased. Now that brings us to something, you think about that and you think reactance is different on an inductor than it is on a capacitor. And what does that do for me? Well, think about when you have components and you want to select a particular frequency. What happens when you take an inductor and put it in series with a capacitor and you increase the frequency? Well, one of them decreases and the other increases. And you lower the frequency and one of them increases and the other decreases. Someplace in there, there's always going to be some kind of reactance. Someplace in there, there's a sweet spot where with the combination of frequency, value of the inductor, and value of the capacitor, the capacitor reactance and the inductor reactance cancel each other out. Mathematically, the reactance is positive for an inductor and negative for a capacitor. So if you put those two in series and you put there's a certain frequency in there in which the two values of reactance cancel each other out, and you have a very low reactance, so a lot of flow through there. That's a sweet spot. That's called resonance. Okay, and you can connect them in series or in Parallel, just the opposite, it increases at that. So what does that mean for us? We'll talk about that a little later. What it means for us, if you think about when we talked about a radio, back at the beginning, we talked about in the very front of the radio, there's an oscillator in there, and it tunes the frequency. Well, what happens, that's how it works in a radio. You have, on the front end of a radio, you have coils, and you have your inductors, and you have capacitors. And there's all these, every radio frequency in the world's coming into your radio. You don't want to listen to all of them at once. So by varying the inductance value and the capacitance value, you can adjust that so that there's only one frequency that it has a low reactance that slips through, or the rest of them all get blocked out. That's how the tuning on the front end of your radio works. We'll talk a little about this a little bit more. I'll give you an example when we talk about antennas. That's called resonance. And resonance is just the spot in which inductive reactance and capacitive reactance cancel each other out, and you get a lot of current flow. So it's good for us, because that's how we can select what frequency we want to use, by taking the right combination of capacitor and the right combination of inductor and putting them together based on the frequency we want to operate in. When you put capacitors in series, remember you put inductors in series and you put resistors in series, they add up. Capacitors are the opposite. Capacitors don't add up. The formula for total capacitance is the reciprocal of the sum of the reciprocals. So 1 over the value of the first capacitor plus 1 over the value of the second capacitor plus 1 over the third on out, and then divide that whole thing into 1. What it means is, for capacitors in series, the total capacitance is always smaller than any single value. Easy way on your test, if you find out you got 100, 150, 200 in series, well, your lowest value is 100. Your answer is always going to be something less than 100. So when you put capacitors in series, if you want to lower capacitance, you need a capacitance and you don't have the one you want, you can put 2 or 3 in series and calculate to get even a lower capacitance. It's just, that's the way resistors work in parallel and inductors work in parallel. Capacitors are just the opposite. And that leads us into the fact that in parallel, they add. And if you kind of want to think about that, remember I said capacitors is dependent on size? The bigger the plates, the more capacity it holds. If you kind of look at this in parallel, these are all connected together, like one big plate through here. And these are all connected together, like one big plate there. So what we did is made a bigger capacitor by putting them in parallel. Transistors. Transistors are our friends today. Integrated circuits. Even though you might see it, integrated circuits have thousands and maybe tens of thousands of little transistors in there that switch off and on. Okay? Or you may have one that's an amplifier that has transistors inside. But transistors they can be used to amplify, or they can be used to switch. You remember on the vacuum tube how we had that grid on the vacuum tube, and it was controlling a big voltage. So whatever little voltage you put on the grid, it allowed the big voltage to flow, and it looked just like it. Okay, transistors work the same way, but they're solid state. So you have small signal transistors, which are little ones. Let's see if we got any on there. I don't think I have. Small signal transistors. It's because they amplify really low value signals like radio frequency signals. And there's also power transistors, which are much larger, and they usually go onto a heat sink to help sink the heat off. Power transistors and both of these can be used for either switches or for amplifiers. So you may have small signal transistors in your radio amplifying the intermediate frequencies in the radio. When it comes time to amplify one for to amplify the signal for the output, you'll have maybe a power transistor. Or if you have an amplifier where you want to amplify the RF output, the radio frequency output of your radio, you'll have big power transistors on that handle a lot of amperage, have a lot of current. But it's composed of semiconductor material, and they have at least 3 terminals on them. The simplest one is the bipolar transistor. And the bipolar transistor comes in 2 versions. It comes in a PNP and an NPN. And it depends on how the material, the sandwich of material inside of the transistor is layered up. Whether it's a P material here, an N material on the base and a P material on the collector, or there's an N material, a P material, and an N material there. We're not getting into transistor theory that very deep, so you won't need to know about those types. But the way you can tell the difference is by which direction they indicate which is a PNP and which is an NPN by this arrow here. Whichever direction the arrow points indicates whether it's a PNP or an NPN. Now, that makes difference on how you put it in the circuit, where you put your positive and negative voltages on this. The easy way to remember it is just remember one of them. NPN, maybe the acronym for that is not pointing in. NPN, not pointing in. If the arrow points out, it's an NPN. It's not pointing in. If the arrow points in, it's not an NPN. It's a PNP. The bipolar transistor, this is where you put the small signal in. Okay, and this is where the large signal comes out. The real powers, the large power is going through here, and this base, from the emitter to the collector, and the base is what's actually controlling it. It's controlling this, either letting it vary, or shutting it off and turning it off and shutting it on. You can use that as a switch. You can turn it off, nothing comes through. You can turn it on, your full power comes through, or you can put a signal in there. And it amplifies that signal uniformly on the other end. So that shows it as an amplifier, but a bipolar transistor can be used as an amplifier or can be used as a switch. We okay so far on this? Okay.
The transistor then is analogous to a vacuum tube. Mm-hmm.
The base is a control grid.
Yeah, the grid is...
might be the base.
Oh yeah, base. I can't read my own handwriting. There we go.
I'm sorry, yeah, base. The emitter would be the cathode, and the collector would be the anode.
Yeah. Good. Thank you.
Transformers. You remember inductors do their business with magnetic fields. Expanding and contracting magnetic fields based on the AC signal, the alternating RF signal coming in. And if you remember earlier, we told you when you had solenoid coils, you had to be careful. If you put them all in line, they would couple with one another, so you wanted to turn them at 90-degree angles. Well, that's when you don't want them to couple. We can also use the inductors, the coils here, we can also use those to our advantage to couple to each other. And one of the ways we do that is with a transformer. And a transformer has a coil called a primary. That's where the source is going in. And a secondary, and that's where the signal's coming out. And the ratio of turns, the number of turns here versus the number of turns there, determines what voltage comes out based on what comes in. It's a ratio. Okay? To make it even better, we put some iron in the middle. Because iron's magnetic. Iron helps concentrate that magnetic field. In a little picture on the top up there, you'll see that we've got an iron core, we've got voltage going in, there's magnetic flux through here, the transformer core, and it induces a magnetic field in here, and makes voltage coming out. That's a power transformer you're seeing there. You probably saw those. Here's a power transformer. This is a laminated core in a kind of a H section here. Primary going in, secondary coming out. This is puts out 16 volts at 4 amps. And it takes 120 volts going in. 120 volts going in and 16 volts going out. If you kind of look at this, you're going to realize that there's a lot more turns in the primary than there are on the secondary. And the size of the wire that's being used and dictates how much current I can put through that. I've got a great big one that puts out about 30 amps I can hardly pick up. It's huge. But the size of the wire, and there's hundreds and hundreds of turns here. So it's the ratio. And you're using magnetic coupling. You're using a coupling of that magnetic field, that magnetic flux. You're coupling that together. And what you're also doing is isolating. This here is never directly connected to that there. This is isolated, and it's only connected to an electric field. So we look at the ratio of the windings. We got the primary and the secondary. Let's say we have 200 turns in the primary and 50 turns in the secondary. What's the ratio of the primary to secondary? 4 to 1. We took the secondary, 1, and 4, because it's 200 to 50 is 200. 50 divided by 200, or 200 divided by 50 is 4 to 1. So if we put 240 volts in, for example, which is 4 to 1 is 25%, and multiply it by 25%, we get 60 volts out. So 200 turns on a 50 turn, a 4 to 1 transformer, and it doesn't make any difference. This could be 400 and 100. The ratio would still be the same. It's the ratio that we're interested in. The ratio of the input, the primary, to the secondary output. That ratio, divide this by that, you get 4 to 1. 4 to 1 is R, which is 1/4, which is a quarter. 240 volts times a quarter times 25% is 60 volts. So this transformer here will convert 240 volts to 60 volts. Also, there's the same thing with impedance. If you remember what impedance is sort of like resistance. It's measured in ohms, but it's also the opposition to the flow of current. But it's complex. It's more than just resistance. It has some inductance in it. It has some capacitance in it. It's a complex, a more complex measurement. Maybe an audio transformer. Maybe your output from your amplifier has real high. Say it has 200-300 ohms resistance. That's the characteristic of that amplifier, and you want to use an 8 ohm speaker on there. So what you would do is you'd put a transformer that has the proper characteristics to it, the proper ratio, so that the output would be 8 ohms. It would step it down to 8 ohms. It's never directly connected. It's isolated, but it still uses that inductive capacitance. So you have 100 ohms impedance on this example coming in, and 50 ohms impedance coming out. Why is that? Because there's 1,000 turns here and 500 turns there. The ratio is a 2 to 1 ratio. So what's 0.5? 100 times 0.5 equals 50. So it's the ratios is always the key. You look at this, take the whatever the primary is and the secondary is, and you divide those two, it's going to be, you could be turned around. You could step up the same way. You could have 50 ohms in your primary and 1,000 ohms in your secondary, and that way it would be twice as much. Instead of being 100 ohm impedance, you'd have 200 ohm impedance coming out. So it can work either way, as long as it's a ratio. It's a ratio of in, it's the ratio out.
One of the questions that just took me by surprise last night, I'm good with that, step up and step down ratios, but one of the questions asked about number of turns, and there was a square root of the impedance involved. Took me by surprise. Let's see. I don't know if I can remember what question it was.
Okay. We'll take a look at that later.
Okay.
But that's how it works. It's the ratio. We talked about impedance. Impedance is also the opposition to alternating current. We think of resistance, pure resistance, as the opposition to DC, but it also works with AC. But impedance is the opposition. It's complex. It includes resistance and reactance. Okay, so it's a complex. You can't, and the thing about it, it varies with frequency. Where resistance, pure resistance, is constant. But when we start throwing capacitance and reactance and capacitance and inductors in there, remember those change with frequency. The circuit includes those and whatever resistance that is in the circuit as well, such as the diameter of the wire and whatever, or physical resistors in the circuit. We end up with something called impedance, which is a more complex resistance or opposition to alternating current in a circuit. And it's also measured in ohms. Matching the source impedance to the load impedance results in the maximum transfer of power. So what you want to make sure that you have is that if you have a load that has an impedance, such as an antenna, that has an impedance of 50 ohms, that you're feeding it with 50 ohm coax, and that the output of your radio is 50 ohms. If you're buying a radio, the output of the antenna is going to be 50 ohms. A coax connector on an antenna is going to be 50 ohms. You want to make sure that your feed line and your antenna are 50 ohms. That way you get the maximum amount of power. If not, you start getting a mismatch. And you start getting some impedance problems where you're not getting the full power out. So what are the real key to all of this is matching the source impedance and the load impedance should be as close to being the same as possible. When they're the same, you get the maximum transfer from your source to your load. That's why we have, let me back up. That's why we call balun and unans. For audio, this is used for in audio, but in antennas, we're talking things about baluns and unans, and they're an acronym for balanced to unbalanced or unbalanced to unbalanced. And what they are is a transformer. Let's say you have an antenna that has a characteristic impedance of 400 ohms, and you have a radio that needs 50 ohms with a piece of 50 ohm coax. Someplace in there, you're going to want to put a transformer that changes your antenna to 50 ohms as well. RF transformer rather than an audio transformer, rather than a power transformer. It's called a balun or an unan. Questions so far? We got some questions here. These are questions out of your question pool. Which of the following components should be added to a capacitor to increase the capacitance? You have a capacitor and you need to increase the capacitance. You add an inductor in series, a resistor in series, another capacitor in parallel, or a capacitor in series. What makes bigger, what addition makes bigger capacitors?
Parallel. See?
Yeah, in parallel. What is impedance? It's a charge stored in a capacitor, inverse of resistance, the opposition to the flow of current in an AC circuit, or the force of repulsion between two similar electric fields. It's the opposition to flow in an AC circuit. It's not pure resistance, even though it's ohms, it's not pure resistance. It's a composite of reactance, which is inductive capacitance and pure resistance. Why is impedance matching important? So the power source can deliver maximum power to the load, so the load will draw minimum power from the source to ensure that there's less resistance than reactance in the circuit, or to ensure that the resistance and reactance of the circuit are equal. A. Get the most power. More power. Remember Tim the Tool Man. Oh, I can't do that. I'm not going to try. Which symbol represents a multiple winding transformer? Think about it. Forget about multiple. Which symbol represents a transformer? And you remember a transformer was two coils, and it usually had an iron core in the middle of it. Which symbol you think?
6.
If you say 6, you're right. Which symbol represents an NPN junction transistor?
2.
2. Why is it an NPN? How do you know it's an NPN?
Not pointing in.
The arrow's not pointing in. Yeah.
It is pointing in.
No?
Well, my eyes
I know. I know. But that's it. 2. The arrow's pointing that way. It's not pointing in. That's an NPN junction transistor. If you get that on your test, you'll get it right. See? What's the RMS voltage across the 500 turn secondary transformer if the 2250 turn primary is connected to 120 volts AC?
So that's going to be on the test. Huh?
That's a test question. Well, it's on the question pool. It may or may not be on the test. It's in the question pool.
26.7.
There you go. Discussion.
I hope there's only one question from this.
I don't remember how many there were from this section. We had,
It's
I
mandated.
think there's 2 or 3.
Yeah. 2 or 3.
But just think about what you know about this stuff. Think about what you learn. Ground. Ground's universal. Everything's relative to ground. Ground's important. Ground's our friend. But don't ever get between voltage and ground. It may be your friend, but don't ever get between it and voltage. It's jealous. Ground's an important factor in electricity, electronics, and radio communications. It's a common reference point. It's a point in which everything is common. It can be physically, it can be the ground, the earth. Or it can be something that represents the earth. It can be the chassis of a radio, for example. Or it can be radials on an antenna or something like that. So it can be something that either represents the earth or the earth itself. In Europe, they don't talk about grounding. They talk about earthing. They don't ground a radio, they earth their radio because they connect it to the earth. We call it ground. There's two different symbols we typically use. Physically, we use the one that kind of looks like a spade. Like you might dig in the ground. That might be like if you're going to dig with a spade, it kind of have a pointed end on it. That's the one that talks about the earth. The other one looks like a pitchfork. That's the one that connects to a chassis, something that's not necessarily earth. This is the common convention. Engineers may use that, or they may use a triangle, or they may use it wrong, but inadvertently. But either of those two symbols indicates ground, and that's important to you. And one of the important things about it is grounding your station. And one of the reasons we ground the station, there's a couple of reasons we ground the station. One of the reasons we ground the station heavily is if you have an antenna outside, you want to make sure that you have lightning protection. The one thing that you need to make sure about your antenna and lightning is that don't let lightning in your house. Don't let it get loose in your house. Believe me, it'll cause you all sorts of problems. Keep it outside. Okay. If you remember about resistance will take, parallel circuit, resistance in a parallel circuit, resistance will travel mostly through the power, or voltage and current will travel mostly through the path of least resistance, the smaller resistor. So what you want to do is you want to have the least amount of resistance outside your house. So that if you're lightning, even though you have a coax cable going inside, you want to make sure you have a nice big fat conductor on the outside so it takes the least path of least resistance, which is to the ground outside your house. It also helps with your antenna. It helps make your antennas more efficient. And it also helps cut down interference on your station. Typically, a flat piece of ribbon or a braid, a copper ribbon or copper braid is the best connector because it's got low resistance, a lot of resistance. And if you remember, lightning has a lot of RF frequencies in it as well as DC frequencies. If you remember back from your technician, there's a thing called skin effect, and that's where all the voltage and current tends to go to the outside of the wire. So the bigger the outside of the wire, the more it'll carry. Okay? AC is kind of the same way. Down through the middle, there's not a lot carried. So the bigger it is, the better. And there's a lot of RF components. And you've heard those RF components in lightning if you're trying to listen to the radio and hear the lightning strike and interfere with your radio. So what you want is a flat ribbon. Flat ribbon's nice because it's not very thick. It's almost all outside connector. Or a braid's the same way. If you got a flat braid, it's a whole mess of small wires in there. Each one that has the current voltage flowing on the current flowing on the outside. Heavy wire, flat ribbon is the best. A heavy wire is second best. It's just as good. If you can't get a flat ribbon connector, then put a big heavy wire on there. And a solid mechanical connection to your ground rod. Multiple ground rods are even better. All ground is not equal. Along the seashore, ground next to a river, where the area is damp, the earth conducts much better than it does in sandy soil, for example. Around here, we don't have really good ground because our soil around here is pretty sandy. So what you want to do to help that is you want to put multiple grounds if you need to, because each one of them is going to have some resistance to the ground. So if you put a couple ground rods out there and connect them together, you'll have a bit more effective ground than a single ground rod. Electrical standards say a ground rod should be 8 feet long. If you can't put an 8-foot long one in the ground like me, I hit rock about 4.5 feet down. What I do is then cut it to half and put 3 or 4 ground rods in there. But it should be 8 feet long. And that's if you're gonna drive the ground rod, you want to be the guy with the hammer, not the guy down below. Okay. Yeah. Yeah. And if I've got the hammer, if I have the hammer with my bad vision, then you don't want to even be near it.
Mike, if you put multiple ground rods in the
heavy
Copper wire.
copper wire or braid or something like that, yeah. Actually, when they talk about a tower, they recommend 3 ground rods around, 3 8-foot around your tower to ground a tower well. Yeah, and just connect them all in series and then hook them up. If you connect them, you want to connect, yeah, if you have 3 of them, of course, you want to connect them both ways. Not daisy chain, you want to connect them in a circular fashion. Don't solder your ground rod, okay? Use a good solid metal conductor. If you remember that when you solder, you take some a tin lead mixture and you heat it up at about 500 or 600 degrees. You heat it up and you melt it on, and it creates an electromechanical bond, okay? You don't want to solder because lightning strikes is much hotter than 500 or 600 degrees. Lightning bolts are thousands of degrees in temperature. I mean, they'll incinerate things. You don't want to do that because if lightning hits, the current, the high current of a lightning strike will just vaporize that solder. Now remember, it's current, not voltage. Voltage doesn't do it. It's the current, the high amount of electricity, of current trying to go through there will just vaporize that. So all of a sudden, and a lightning strike typically is not a single strike. A lightning strike is typically multiple strikes. And a lightning strike usually strikes from 2 directions. It strikes up and down at the same time and meets in the middle, and then it just, maybe you'll see 2 or 3 strikes hit. They're fast enough, the persistence of your eye and the ionization of the air, you don't necessarily see the number of strikes, but there are multiple strikes. So what'll happen is it'll burn your solder off on the first strike, and then before it's finished with its business, striking 2 or 3 more times, you've got no ground. And I can testify to that. I woke up about 6 o'clock one morning. We had a storm, and saw this flash outside the window and heard an immediate thunderclap. That lightning strike is really, really, really close. They were simultaneous. That thing was probably within hundreds of feet of me. So lights were still on. Turned the lights on. Lights were still on. No problem at all. My wife gets up first. She goes out and says, "I can't get the coffee maker to come out in the kitchen." She says, "The outlets don't work. Something's wrong here." So I go out. Sure enough, it tripped the breaker. I thought, well, it was induced some into the house, and there's a ground rod sticking in the ground right outside of my electrical box where it comes in. So I flipped the breaker and it went right back off immediately. It tripped right back off. There's a short someplace. So I spent a week taking things apart. It powered the electrical sockets and a range hood over the top of the range. And I took the range hood down because I couldn't figure out what it was. I took it apart. Disconnected all the even with everything disconnected. I took all the load off. The breaker was still break. There was nothing connected to it, and I couldn't figure out what it was. I'm going around and around and around. And next to the stove, my wife had installed what's called a pot filler, which is a faucet with a gooseneck type thing on it where you could actually fill pots with water on the stove. It has water to it. And I was just messing around with my ohm meter, and I put my hand, one of the leads, what they had the lead in, I just grabbed the whole of that thing for support and started back, and I realized I had a short between my electrical wire and the pipe, the water pipe. What had happened in the house, when it came down, it went to the stove hood, and then it went around went to the electrical box and went out to the stove hood and around to the sockets and down the wall. When the plumber came in to install the pipe for that copper pipe for that faucet, for that pot filler, he went horizontally through the wall, and the electrical wire laid up against the side of that copper pipe. Now it's Romex, it's got an insulator on it and everything. Actually, it has the insulator on the wire, and it has a sheathing on the outside and the paper on the inside. What happened was the electrical ground rod outside was not good enough, and lightning got in the house. And that was the closest electrical outlet I had to the fuse box coming in, to the meter. And it jumped the gap, burned through the insulation, all the insulation, and welded the wire onto my pipe, and found the ground right there. So it never got any farther in the house than that. But lightning did get in my house, and it didn't burn anything else out. It just grounded right there. It's all the farther it went. But you want to keep lightning out of your house. And other people have had, my father They had their house. They were an area that was lightning prone, and something would get hit in their yard at least 2 or 3 times a year. And they had a well pump down in the ground, about 150 feet down. They had a pump, and they kept losing the well pump because the wire, it would hit something on the electrical wires, and the first best ground it found was down the well into the pump. It would kill their well pump, and then they had to pull 150 feet of pipe out. But on their house, they had an electrical timer on an outside light one time, and it blew the timer off the wall. It totally killed a tree, skinned a tree, but you don't want lightning into your house. So the moral of that story is the ground's very important to you to keep lightning out of your house, and for other reasons we'll talk about in just a minute, which is grounding all your components. You can't do this for your handy-talkie. It's just not going to work. I mean, you're not going to ever have a wire long enough that you can go any place that you can ground it. So you don't. But you don't worry about it. Odds are good. Lightning's not going to hit that. And you're not going to have much interference. But for well, you've got a fairly complex HF station where you maybe have a transceiver and a transmatch or an antenna tuner and a keyer and an antenna switch or maybe 2 or 3 radios and things like that. They all need to be grounded to reference to the outside. They really need to go to reference ground. Don't ground them to the ground on your power line. Even though you may have a 3-prong plug and it connects to the chassis here, don't get your primary grounding through your power plug. That runs all the way through the house. And it might be long enough to be an antenna. What you want to do is use an outside ground and connect all these to a common point. Don't string them together. Good common point, good way that ARRL says is get a piece of about 1/2-inch copper pipe. Use that as a common ground, hook one end of it to the rod on the outside, and then ground everything else to that same common location. Or you can you can make a little clover or flower thing where you put a lug on the wall and connect all of them to those if you want. But connect those all to a common point. Stay away from the 3-way ground in your electrical system in your house. And keep this as low, as big as possible. Keep these ground wires as big as possible. Your connection as good as possible, and keep this as short as you can be. That's where you've got a good ground system, a single common point, and that common point being that piece of copper. You could also, if you want to pay $70 or $80, you could buy a commercial piece of flat copper that has some lugs in it, and it'll work just the same, but it's just going to cost you about 10 times as much. What you don't want to do is you don't want to daisy chain these things together. You don't want to hook to your transceiver, then to your transmatch, then to your keyer, then your antenna switch. Each one of these has resistance, and the next thing you know, because of resistance, this thing here ends up being above ground because now you got resistance between it and the ground. So it's above ground potential. Each of these are at a different potential. What you'll end up with is you're going to end up with hum and distortion in your signal. So you want to keep everything in and don't daisy chain them together. Also avoid a long wire here. Keep this wire as short as possible. If it's too long and it has resistance in it, it could actually become an antenna. It could radiate as well. So avoid a long ground wire run because it may end up being resonant on some frequency. Remember resonance, all of a sudden there's a frequency here in which it has no resistance and it loves to radiate on that. So you want to avoid hum and distortion in your signal. And that's called a ground loop, is what it's called. It's an area where you're daisy chaining these together, where you're ending up with some components that are at a higher resistance potential above ground than the other. That's called a ground loop. And ground loops will cause hum and distortion. If you're talking to somebody on the radio and they go, you got a lot of hum in your signal, you probably have a ground loop. Sometimes RF may get back into your microphone. That causes the same thing. But hum and distortion is typically as a result of a ground loop, from having something above ground. Or having no ground sometimes. That kind of, and that's an interference internally. There's other interferences. Your radio may interfere with other devices. Your radio may interfere with a stereo system, with an audio system. Your radio may interfere with a landline, a wired telephone. Your radio may interfere with that. Even when you're operating clean and exactly on your frequency. When you're operating on your frequency bands, when your signal is clean, even at that point in time, you may interfere with other devices. And usually that device, or television sometimes, but those other, usually the fault are those other devices. Usually your speaker cords are acting like an antenna. The cord that goes from your radio, from your amplifier to your speaker on your music at home, your audio devices, acts like an antenna. That's usually the fault of the equipment, that it's not properly designed and not properly shielded. And if you remember back from your technician license, it's the owner's responsibility to deal with that. That's their problem, but good politics says you'll help them do that. Okay? Because they'll end up calling the police or calling FCC or somebody. But how do you know whether it's interference? Well, if you're operating phone, if you're operating voice, what you'll hear is possibly what sounds like your voice on the radio, or sounds like your voice on a telephone, but it's distorted, it's jumbled. I used to have problems with the computer speakers on one of my computers, my desktop computers, when I operate on 6 meters. I'd key up and talk on 6 meters, and I'd hear myself garbled in the speaker on the computer across the room. I put a couple filters in the, wound some chokes, put a couple coils, a couple filters in the speaker wires, and the problem went away. If you're operating Morse code, you're going to hear this clicking on off, starting in cadence with what you're sending, dots and dashes. It's going to be a click or a hum on a nearby device. Use a bypass capacitor on the speaker leads, or use a ferrite choke on the cables, or things like that. That's one of the ways that you can eliminate or reduce that to the point where it's tolerable. You might get interference. Something might interfere with you. We operate, as long as you're in ham bands, we operate in a band that, except for those ones that we share on a secondary basis, is exclusively licensed to our use. And no one else is supposed to be using that. For all practical purposes, nobody else is supposed to be using that. For sake of argument, we'll say that. That doesn't mean something's not going to interfere with you. One of the most common kinds of interference is power line interference. Back in the early days, back before there was exotic tuned circuits and everything, the early days of radio, they used what's called a spark gap transmitter. And they produced a radio wave. Miniature lightning bolt. High voltage, miniature lightning bolt. They'd use a CW, they'd turn that thing off and on. And if you ever heard it, it was just as raspy and horrible sound as possible, and it covered half the HF band sometimes, because it was just like a lightning strike. It was really rich in harmonics. So it was a wide frequency band. But there wasn't many hams out there at the time. There were only very few radio stations, so they didn't make much difference. You know, you sat and you took up the 40-meter band and the 30-meter band on the 60-meter band all at the same time. No big deal. Nobody else was on it. As more people came on, then they had to refine this and come up with something better. Well, power lines is a big offender now. They're just like a spark gap transmitter. There may be some arcing in there. If they don't have good connections, you'll get some electrical arcings that cover all sorts of frequencies and produce radio interference that's very rich in harmonics. One of our VEs here, his neighborhood is full, literally full of RF from arcing power lines, and he's got power lines on the street side, on one side of the street across from him. He's got power lines to his backyard. You can take a shortwave radio and stand in the middle of his yard and hear just a little bit of noise, and if you walk towards the street, it gets louder. If you walk towards the power lines in the back, it gets louder. It's just full of just RF radiation. The noise blanker on his radio, his digital signal processor, remember we talked about digital signal processors back there, where they'll take that signal, computerize it, clean it up to however you want it cleaned up, alter it and send it out. He can get most of that out with his digital signal processor, so he can still hear. He has been no sympathy whatsoever from the electrical companies. They send people out that don't even understand what they're doing, much less what he needs, and he's had no result, no relief from that whatsoever. But there's probably 2-block area around him that's just rich. And once this thing starts arcing, it broadcasts it into that big long antenna, that big wire run along the top. So it works as an antenna. You got a transmitter and an antenna with arcing power line. That's receiver interference. There's not a whole lot you can do with that except try to track it down, get some people that can help you with a direction finder, call the power company, and have them come and fix it if they will. We'll talk about gain and loss. When we talk about antennas, we talk about amplifiers. We talked about amplifiers, we say gain. And amplifiers, what was gain? Well, that was the ratio of the power in to the power out. How effective that was. Gain is usually discussed or described using the decibel. dB. We call it dB. We don't call it decibel. We call it dB. A decibel is a ratio. It's simply a ratio. The math, you won't have to do the math on the test, but we'll show you what the math is because you can do it. It's the ratio of whatever you're comparing it, the things you're comparing it to. And we talk about power. Okay, we'll talk about power here. P1 to P2. Whatever my P1 is, whatever my P2 is, I take the ratio of those, and it's multiplied times 10 times the log. So I take the log of that, multiply it by 10, and that gives me a dB. We typically look more in a table like this. We typically round this stuff off. The nice thing about that is you could, if you have various components such as your radio, your antenna has gain, your coax may have loss, they're all expressed in dB. You can add and subtract these things and come up with a final number without doing any fancy math once you have these simple numbers here. Remember that multiplication factor is an X is a times factor. So the ratio is, for example, if the ratio is 2 to 1, if my gain is 2, my dB is 3. Now remember, this is logarithmic. This is not linear. So it kind of looks like logarithmic all of a sudden and linear, and then all of a sudden goes off the scale. A power increase of 2 is a 3 dB gain. A power decrease of 2 is a 3 dB loss, 2 times. A power increase of 4 times is a 6 dB gain. No power increase, it's the same as a 0. 10 dB is 10 times increase. 20 dB is 100 times decrease. 30 dB is 1,000 times increase or decrease. The ones you'll be typically looking at are in here. This is usually the range that you see for antennas and feed line and things like that. But remember, it's a ratio. dB is a ratio. dB is this compared to that. And we use the dB as a handy factor that eliminates a lot of math once you've got the dB. Antennas, if you're going to buy an antenna, they'll usually tell you what the dB gain is. We'll talk about coaxes a little later. They'll tell you what the dB loss is in a coax. So all you have to do if you're looking at taking an antenna system, you take, well, how much do I have in my antenna, in my coax? How much do I have in my antenna? What kind of power should I expect to get out? So, it's nice. If you got a 100-watt transmitter and your antenna system has a 3 dB gain, you get the equivalent of 200 watts out. Nice. Let's talk about antennas. The simplest antenna in the world. I'm going to need you to help me on this. This is the simplest antenna, the simplest practical antenna. Oh boy. I'll let you untangle that one with them. The simplest practical antenna is a dipole. The dipole, essentially in the real world, is what we compare all the other antennas to. Now we'll talk, there's a scientific thing that they do too, but we won't talk. We're talking about dipoles, so we're going to talk about real world stuff. It's a half wavelength long. Okay. Remember, wavelength is a function of frequency. Frequency is a function of wavelength. It's a half wavelength long, and it's fed in the middle. That's what makes it a dipole. Di meaning 2. So if that's a half wavelength long, how long is that leg right there?
How long is what?
If this is a half wavelength end to end, how long is it to the middle? Quarter, right? Same thing here, quarter. The simplest antenna is a quarter. We have a dipole right here. In the middle is where I connect my antenna to. There's my feed line. These two ends are equal. And I have a dipole antenna. And it's a function of wavelength. a function of frequency. How long, what frequency do you think this dipole works on?
So it's about 2 meters
Here.
here and 2 meters there, makes 4.
Let's measure that. And
12.
measure it end to end.
6, I'll go with 6.
Okay. It's about 9.5 feet. Okay. About 9.5 feet long. Okay. So which means what for a, what is it for a quarter wave? Yeah. About 4 foot 8 inches. Okay. 9.5 feet long. You're going to guess what? You said 6?
I think it's 6.
Okay, 6 meters. Let's do it just a swag. No, we won't do it scientifically. Let's do a swag. 6 meters is how long? What's half of 6 meters?
3 meters.
3 meters. How long is 3 meters?
3 yards. Getting a little long.
A little over 9, right?
Yeah.
A meter's a little over, yeah. How much did we say this was? 9.5 feet?
It's 3 yards.
Yeah.
Okay.
So it's a 6 meter antenna.
Yes.
That's how it works. It's that simple. To be more precise, thank you. To be more precise, we need to, there's another formula we can use. You've seen that. 468 divided by the frequency. Remember that one from your technician days? 468 divided by the frequency. Optimally, you want to have it a quarter wavelength off the ground. So what's the minimum distance you want to try to put this from the ground?
4.5 feet.
Yeah, all right, well, yeah, it's going to be, what, 6 meters? Quarter of 6 meters? Now we're at 3 meters, meter and a half, about 4.5 feet. Yeah, so as long as you're more than 4.5 feet off the ground. Now that's not bad on 6 meters. What about 40 meters? What happens if that's a 40 meter antenna? How long is this going to be on 40 meters, roughly?
20 meters.
20 meters long. How far should it be above the ground?
10 meters.
10 meters. How long as far as 10 meters? About
10 yards.
33 feet, something like that, yeah. So it needs to be a little higher off the ground. There's a reason for that. And the reason, you can put them at any height you want. But at the optimal height, or higher, it has pretty much an omnidirectional, oh, well, it's just directional. Let's hold this up again, Chris. We'll talk about directional. Okay. It's pretty much omnidirectional this way, but it's directional this way and that way. But it's a pretty round pattern, okay? This is a directional antenna. This transmits equally well this way as it does that way. It doesn't transmit and receive very well far off the end, off the end. So I want to if I want to talk to most of the United States from where we are here, I run it north and south, so I talk east and west because we're about in the middle.
Think of it as a figure 8.
Yeah, it looks like a figure 8 type pattern. So and it's talks pretty good. It's got a pretty good radiation pattern on it at a quarter of wavelength off the ground, and it has pretty close to a 50 ohm impedance here. Actually, it's 72 ohms, but it has pretty close to a 50 ohm impedance, which is close enough. That's not bad. So that's our optimal. That's the optimal antenna. Now, what happens if we lower it? What happens if we lower it closer to the ground? It still works. Not a problem, it still works. However, the feed point resistance, the feed point is going to decrease. The impedance at the feed point is going to decrease. Also, the radiation pattern is going to be forced upward. So it's not going to radiate as well this way, as effectively this way as it did. It's going to start radiating higher towards the sky. So it changes the radiation pattern as well. So when I lower it down, it decreases the feed point impedance with the decrease in height above ground, and it raises the height of the radiation takeoff pattern. Well, that sometimes is good. Remember skip? Remember we talked about the skip zone? Skip zone was where you're in that spot where the radio wave, the radiation pattern took off and went over your head. You were past the horizon and went over your head, bounced off the ionosphere above you and someplace else in the world, and you couldn't hear those people. Well, what I want to do, let's say I'm on 40 meters, what do I want to do if I want to talk locally? If I want to talk to Oklahoma City, well, Oklahoma City is over the horizon right now. I'm going to skip over that all the time. One of the things I can do is I can make what's called an NVIS antenna. NVIS stands for Near Vertical Incidence Skywave. It depends on skywave propagation. It depends on refracting off the ionosphere. But what I did is I lowered my antenna down real low to the ground. And I forced that antenna pattern, that radiation pattern, up into the air, up above me. Almost like spraying a garden hose up on the ceiling. It's going to spray out around the sides. So I use an NVIS antenna to talk locally, to minimize my skip. That's not a very good long distance antenna, but if I don't want to talk long distance, then I want to talk, for example, let's say it's the radio station at the Red Cross building in Fort Worth. Red Cross probably doesn't want to talk to Europe. Red Cross, if they need help, wants to talk probably to Oklahoma City, Joplin, places like that, Houston, Austin. They want to talk locally. They want to talk in their region, in their area. So they don't want an antenna that's going to shoot out to Europe and they can't hear them. They want to use an NVIS antenna, so they're going to mount their antenna that they're going to use in such a manner that it talks locally only, sprays up on the air. But remember, what happens is the feed point impedance keeps getting lower and lower and lower until it gets down to the point where my radio don't like it anymore. There's a trick. On this dipole antenna, let me back up to the dipole. On the dipole antenna, my feed point impedance, lowest feed point impedance is right here. That's my lowest feed point impedance. And impedance is determined by the length of the antenna. It gets higher as I go up here. It gets higher as I move off the center. If I didn't terminate this antenna right there in the center, my dipole right in the center, it would be higher than the impedance I wanted. Well, I could use that to my advantage. It got lower than I wanted it. So what I'm going to do is I'm going to offset my feed point just a little bit till I find a sweet spot on my antenna where it gets to be 50 ohms. Maybe it's only 20, 22 ohms right here or something like that. Well, I can put a transformer in there, or I can just offset that just a little bit till I find that 50 ohm spot on there. Typically an NVIS antenna, you'll see it's down to even a 10th wavelength above the ground. Okay? With the feed point offset to compensate for it. NVIS antenna works on 75, 80, 60, and 40 meters only. It's really not effective on any frequencies higher than that. Now, what about if I want to operate more than one band on my antenna? Remember my feed point impedance? My antenna is cut for a certain length.
But that one's not flexible at all, right? You're stuck with those two lengths you got.
So I'm stuck with 6 meters. Well, I make a second antenna, or third antenna, or fourth antenna. Or I start making use of resonance, inductive and capacitive reactance, and I make some things called traps. I take the highest band I want to operate on, 20 meters, and I cut it for 20 meters long, essentially, for 20 meters. They'll need a little bit of modification because those traps do have some effect on it, but essentially for talking purposes, we're going to make an antenna 20 meters long. And I have my traps, and these have inductors and capacitors in those traps, and I adjust those inductors and capacitors in that traps so that they have a very low resistance, extremely low resistance to RF current. So on 20 meters, that becomes invisible. That becomes invisible. And what my transmitter sees is the entire length of the antenna, a 20 meter long antenna. However, it's adjusted so the fact that when I go to 15 meters, this one here's got a high resistance of 15 meters. That one has a high resistance of 15 meters. So it only sees the length 15 meters long. Okay. I go to 10 meters. I've got them set so that it doesn't like those. This puts a high reactance, a high opposition to the RF current flow. So I only see the piece that's 10 meters long. That's a trap dipole antenna. That's a multi-band antenna. They automatically change the RF length of the antenna based on the frequency. Works cool.
Is that, I have a Kenwood THF6A. It's got a little bulgy thing up on the rubber duck antenna. Is that what that little bulgy thing is? It's a trap? Because I have the 3 bands, 2
Yeah.
meters and 440.
Absolutely, absolutely. So it's using the short part of the antenna for one of the bands, and it's using the whole antenna for the other part of the band. That all makes sense?
Yeah.
There's a downside of this. What's the downside? That was a
It
question.
doesn't work very well.
Well, yeah, they do induce some loss, okay, but they're not bad. What's the real downside of that, though, based on what you learned from your technician license?
Yeah, it's subject to harmonics.
Right. I might be transmitting on 20 meters. 10 meters is a harmonic of that. If my radio's not real clean and putting out harmonics, if I had just a 20 meter antenna, the harmonic would get up to the antenna and say, oh, I've got it sees a high impedance to that, so it wouldn't radiate. Now I've got this thing fixed up so it can radiate on 3 bands at once if it wants to. So yes, they are prone to radiate harmonics if your radio puts out harmonics. Most new, well-maintained radios, that's not a problem, but it's not, you can't preclude that. Let's talk about directional antenna. We talked about a dipole radiating off both sides. What if I take a dipole here and I want to increase the radiation in one direction? I want to increase the relative gain, okay, in one direction. So what I want to do is I got my dipole here, it's a half wavelength long. Some distance behind on the back side, and the back side being opposite the direction I want to increase my radiation, I'm going to put another piece that's a little longer than a half wavelength, maybe 5% longer. I'm going to space that back there. That's one way. What that does is it causes, it does what it says it does. It reflects the RF and adds it to the RF going this way. So now I get the direction of my radiation is that way, opposite the reflector, and hardly any this way, or not much that way. So a director can cause that to focus beam antenna. Remember beam antenna? To focus a beam of radio waves. Or I can use a director. A director somewhat is like a lens. It's about 5% shorter, thereabouts. It goes on the front side with regards to the direction of radiation. It goes on the front side, and it causes the radiation to go that way. So I got 2 options. I got a lens like on my flashlight. I've got a lens in the back to push all the photons, all my light forward, and I've got a reflector on the back. A reflector on the back to push all my photons forward, and I've got a lens in the front to focus them down even smaller. And if I put those 2 together, I can have a multiple beam antenna where I've got a reflector and a driven element, and then a director on the end. That's called, we call it a Yagi antenna. Most Yagi antennas that we talk about are usually 3 elements. They kind of use that as a rough comparison. That's a common antenna, so we kind of use that as a rough comparison. All right. The gain, the forward gain on this antenna is 9.7 dBi compared to a dipole in free space. So if I had a dipole, and that's about 9 times the effective power. Now that's only in the direction of the maximum radiation, but that's what I want. It doesn't have any negative gain in that direction. Most of my gain going that way. So I get about 9.7 dBi compared to a dipole in free space. And here's something that you may not have seen before. We talked about dB. Remember, decibels is the ratio. It's a comparison. You're comparing something. So the ratio is, what do I get out of here compared to what I only get from a dipole? That's how my ratio came about. Take a dipole, and what do I get here with this configuration? So that's how my gain is figured out. It's about 9.7 dBi. But here's the kicker. See this thing here? We've got a modifier. See the I on the end? That tells you something about the measurement that I'm taking. That's dB as compared to an isotropic radiator. Okay. An isotropic radiator is the things that scientists use to do their calculations. An isotropic radiator is a theoretical radiator. It's a dipole or a point radiator, a dipole with no physical size, think of it that way, out in free space with nothing around it and nothing to affect it. It's the purest antenna in the world, and there's no such thing. You can't buy a DBI antenna. You know, it's theoretical. But it's great for scientists. We usually use DBD. We usually compare it to a dipole. That's why I said a dipole is a reference, because a dipole has about 2.3 gain over an isotropic radiator. So, but this is DBI. But remember, it's about time times the dipole in free space. So a DBI, that's kind of something that you, when you're looking at antennas, when you're looking at how they're advertised, if it advertises as in dB, you don't know what the gain is relative to. They don't tell you whether they use DBI or DBD. They let you guess. It's a marketing trick. It's probably DBI. If they say DBI, we've got to recognize that it's not as good. If you had to compare that with having a dipole, it's not as good as you think it is with regards to a dipole, because the dipole already has gain over an isotropic radiator. Oh, one of the things we talked about too here. Let me back up. Yeah. Feed point impedance. The distance between the reflectors and the director and the driven element also affects the feed point impedance. I can change the feed point impedance. If I have a feed point impedance in here that, say, when I put the antenna together and it's about 22 ohms or something like that, which is lower than what I want, I can adjust it by moving this reflectors and directors back and forth. They influence that. They always, obviously influence it because they're causing the radiation to change direction. So the feed point impedance changes with regards to the distance between the reflectors and the directors and the driven element on there. Directional antennas, forward gain is, how do you increase forward gain? Add more directors. Every director that you put on here increases the gain somewhat. What it does is it makes it no free lunch. It makes it more focused and keeps continuing to focus that more and more. It's like adding multiple lenses in front of your light. It increases the directivity of the antenna, which is what you want. The good thing about that is you can talk and hear good in this direction. You don't talk and hear good in the opposite direction, but maybe you might not want to because you might have interference in the other direction. So this essentially kind of amplifies the effectiveness of your antenna. You can also increase the spacing between all these. But remember, if I increase the spacing between all of these, I may change the driven element to the point where I have to do something different here. I may have to put some kind of matching section in here. We look at Yagi antennas. I'll show you Yagi antennas. Okay. Yep, right over here. A couple different kinds. This one here is a tape measure antenna. This is made out of pieces of tape measure. Typically people use this because they can do what I'm doing just right now. They can fold it up, it's small. They use this for direction finding. Remember we talked about direction finding earlier? The official observers use it and they do direction finding hunts. This is great if you're hunting doing a fox hunt and it's out in the woods and you can go crashing through the woods and hit those with the trees and things like that. That's fine. So what frequency, what band do you think that works on?
2 meters.
Yeah, it's about 19 inches there, right? It's about a quarter wave. It's a 2 meter antenna. The direction, the distance between these to get the gain I want affects the impedance here. And the impedance is not quite 50 ohms like my cable is. So they put what's called a hairpin matching section on here. And this is cut to a size, this is a matching section. It's called a hairpin matching section. It's a delay, it's a line, a delay line. It changes the impedance of the antenna from what it was to makes it about 50 ohms.
Doesn't it short out the tube?
No, it doesn't, because that's a low current point right there. The middle of my antenna has a low current point.
And you're giving it some help there.
Yeah, so it doesn't see ground. Here's another kind of antenna. This is another Yagi antenna. This one has 4 radiators on the directors on the front and one reflector on the back. What frequency band do you think that works on?
UHF, I think.
Yeah, it's about 6 inches long there. You'll find that 6 inches is about 70 centimeters. This is what's called a cheap Yagi. I got more money in that connector than I got in the rest of the antenna. It's a piece of wood and it's some welding rod.
Now, how close do your tolerances have to be drilling holes there? If you're off by, a 1/16 of an inch here or there?
The guy that does these, that developed these, that really perfected these, Kent Britton, he lives down in Grand Prairie, WB5 VJB. He has a website and he talks about all this, and he's an RF engineer, an antenna engineer. He does that for a living. And he has a very non-academic style on his publications. And he tells you that this antenna could be better if he required all the tolerances to be held a whole lot tighter. He said, but you'll never know the difference on the air. It's, a 1/10 of a dB or something like that. So it's not really critical. 1/16 of an inch is fine on these antennas. It's not a problem at all. That's why they're so neat. This has a different kind of matching section here. This matching section is actually, I think, a 200 ohm matching section. The characteristic impedance of this is 200 ohms, but he adjusts that by moving the reflector closer or farther away. So he publishes plans to tell you exactly how far these are, how long each one of these needs to be. This is a UHF antenna.
So the driven element here, this is all one, the
Yep.
top guy is all
Yep.
one piece. But this is the same thing you had on the other one.
Right.
It's shorting it out essentially, but it's
Yeah.
just giving you a parallel resistance.
That's right.
So-
Yeah, because at the center there, on that kind of that type of antenna, the center of it is
You did a pretty good job, up and down. What did you say the guy's name is? With the
Kent Britton,
and-
Brittan.
Like Great Britain.
Yeah. Mm-hmm.
And what's his call sign?
WB5 VJB, Victor Juliet Bravo.
WB5.
Victor Juliet Bravo. Juliet, yeah. Juliet Bravo.
Bravo.
Mm-hmm. And and if you want to Google him online, look up Cheap Yagi. That's what he calls them, cheap Yagis. Mm-hmm. Very interesting to look at that. And he's published several articles in the ham radio magazines over the years. He's a very interesting fellow. If you go to the Ham Fest, he'll probably be at the local Ham Fest. He has antennas made out of printed circuit boards and all sorts of stuff. Those are more for gigahertz frequencies. Questions on a beam antenna? We're going to talk about, we talked about, this is the ideal, what we want our pattern, our radiation pattern to look like. We want most of our radiation going out of the front of the antenna. We would like none, but if we can help it, but we don't usually get that. Very little going out the back side of the antenna. So that's the front radiation pattern, that's the back radiation pattern, and both of those are measured in dB. The one in the front of the antenna is called the main lobe. It has kind of a lobe shape to it. Depending on how many elements you have in the front depends on how wide this thing is. Depending on the spacing between the elements depends on how wide this pattern is. Radiation out the back is called the rear lobe. The gain, what do you think the gain is? Remember, gain is a ratio. What do you think the gain is?
Front to back.
The gain is that's the front to back ratio. It measures the gain. The front in dB divided by the back in dB. If I got, what did we say, 9.7 dBi? Well, this will be a dBi too. 9.7 dBi in the back, and let's say I got one in the back, one in the front, and I got 1 dBi in the back. What's my ratio? 9.7 to 1? Yeah. There's another antenna. You probably saw these up on your roof if you had a television antenna. It's called a log periodic antenna. That antenna, all of the elements are connected together, but they're staggered. This element's connected to one side of your feed line, that to the other, then it staggers over and the opposite here, and they're staggered, alternates back and forth. The shape, the length, and the distance between is a logarithmic mathematical function. Okay. And it's fed at the forward end, at the main lobe end. It's fed at the feed point, goes up in that end right there. The advantage to a log periodic antenna, and you have to calculate this, it's not as easy as making a Yagi, because you can almost guess at one of those and play with it till you get it right or get it suitable. This takes significant mathematical computation to get that. There's Autoline formulas out there. But the advantage of that is wide bandwidth. And that's why they had them on your television set. Your television antenna used to look like that. Because your television band started in the VHF band and went way up into the UHF band. Remember you had VHF frequencies and UHF frequencies? You ever think about that? You all got them off the same antenna. How did that work? Because it had an antenna that had a very high, wide bandwidth. That's the advantage. Not a lot of gain. You're not going to get a lot of gain out of this antenna. There's no free lunch. You're going to get a trade-off. You're going to trade bandwidth for gain. But that's okay. It beats having 3 or 4 antennas on your roof if that's what you need. And usually the television antennas had multiple kilowatts of power coming out, so you didn't have to worry too much about it. But you can also use these, and there's also log periodic ham antennas. One of them out that's typically a lot of people use, a commercially manufactured one that's not very expensive, is called the elk antenna, like, elk. Elk antenna is designed for 2 meters and 70 centimeters. That's its limits. It goes from 2 meters to 70 centimeters. It doesn't go lower than that, doesn't really go higher than that. But it's a great antenna because you have two bands on one antenna, and it's fairly easy. It's compact and it's fairly easy to use. Another kind of antenna called a quad. These used to be very popular antennas on HF. I don't see them much on HF anymore. The quad antenna is a full wavelength from start on your feed line. From here all the way around is a full wavelength long. On 20 meters, that's 20 meters long all the way around. And each side is a quarter wavelength. 5, 10, 15, 20 meters on your driven element. So, what's 5 meters?
15 feet.
About 15, 16 feet, something like that. Not unreasonable for an antenna up on top of your house in a tower. What they usually had is, in the old days, they had an X in here, had a boom in the middle, had bamboo spreaders, and they connected the wire like that on the bamboo spreaders. Behind it, a quarter wavelength behind it, about 15 feet behind, they had another one, which was a reflector. It was about 5% longer. So it was 20 meters plus about 5%. The forward gain on that is about the same as a 3-element Yagi.
So it's sending towards us.
Towards us.
Towards
Right,
us.
towards us. And there's not really a break here. I just did that to show that this is in front of that there. Okay. Quad antennas was pretty popular. They're reasonable on 2 meters and 70 centimeters. They're reasonable to make. They're not hard to make at all. It becomes a very short antenna, a very small antenna. Good gain, but people typically like to make beam antennas because there's less mechanical work involved in making a Yagi antenna. I just had one boom with some holes drilled through it. I didn't have to make spreaders out and all this kind of stuff. And you can see on the tape measure antenna, I'd fold that sucker right up. I would not want to carry one of these through the woods on a quad antenna through the woods on a fox hunt. You can change the polarization by changing the feed point. That one back here was a horizontally polarized antenna. This one up here was a vertically polarized antenna. And we're going to talk about polarization in a little bit later, show you a polarization example when we talk about field strength meters. We'll show you why. If you don't know why polarization is important, we'll show you. There's yet another antenna called the delta loop. The delta loop simply was a triangular shaped antenna. Still a full wavelength all the way around. But now we had a third wavelength, third wavelength, third wavelength. Still a quarter wavelength apart. Just like the quad, horizontal polarization would be here for feed point here for horizontal polarization. Turn it 90 degrees, feed point would be over there for vertical polarization. Reflector is on the back, a quarter wavelength on the back, still about 5% larger. It has a gain about the same as about a 2-element quad, not a 3-element. It has a 2-element quad. Its gain is the same as a 2-element quad, which is the same as a 3-element Yagi. Or this has a gain like a 3-element Yagi. No sense making this simple. I'm following the lead of some of the questions in the question pool. Another antenna, called a Beveridge antenna. Unless you're a shortwave listener, or unless you're a DX, long distance operator, that tends to concentrate on a certain part of the world, this antenna is probably not any real use to you. But it's good for what it does. This is primarily a receive antenna. The losses of this antenna are way too high to use as a transmitting antenna. But it's a great receiving antenna. Its gain is in this direction, in the direction of the feed point. You're about 0.3 to 4 meters. Its height is variable here. A quarter, 1 to 4 wavelengths long. A terminating resistor on the opposite end from the feed point of 100 to 2,000 ohms, and all this you adjust. And it's based above ground. And it receives great from that direction. Fantastic receive antenna, very, very low noise. Because it's grounded to that resistor on the end, you have and it's grounded here on the other side of your feed point, you have very, very low noise. The terminating resistor gets it up above the ground potential. Very, very low noise, very highly directional. So if you had someplace, if you consistently talk to Europe, that's all you were worried about was talking to Europe, you'd have an antenna switch or a separate transmitter and receiver, and you would receive on this antenna, and you'd put that feed point to the east, this terminator resistor to the west, size that antenna up, and you'd be a great receiving antenna to Europe. Probably hear stuff that nobody else could hear. You can't transmit on because it's very low efficiency. It's almost like a dummy load. So you'd be having another antenna to transmit on. But if that's the exercise you want to go through, if you're a shortwave listener, sometimes shortwave listeners have 2 or 3 of these built in their yard. These are huge. Sometimes they're 4 wavelengths long. Depending on the height and everything, it can be as much as 4 wavelengths long. You have a lot of real estate, but you could have 2 or 3 of those if you're a big shortwave listener, and that's what you do. You'd have one pointed to Europe and one pointed to the West and one pointed maybe to South America or something like that. But the Beveridge antenna is primarily a receive antenna.
Why do they call it a Beveridge antenna?
The guy who invented it, his name was Beveridge.
Mr. Beveridge.
His name was Beveridge.
Like Mr. Beer or something.
That was it. Yeah, Mr. Beveridge.
Now, he said that those are huge antennas, 1 to 4 wavelength. Imagine 160 meters
Yeah.
times 4.
And how do you keep from tripping over the thing is the next question.
Well, that's when you got a lot of stuff. The same way you keep from tripping over your radials and tripping over your guidelines and stuff like that if you have antennas in the backyard.
Not very practical.
Mm-hmm. Field strength meter. Okay. A field strength meter is a device for measuring the strength of a radio field. I have a field strength meter here. I have a combination meter. It does a lot of things. Right now it's set on field strength. Okay. Right now it's set on field strength. It does a lot of things. Can I borrow your radio? Oh, you want to key it up with your radio? You know, you need to come and stand about right here. Put it on simplex and key it up. We're just going to measure. It measures the intensity of an RF field. You can use it to adjust your transmitter or receiver.
Biovisual testing.
Okay. Come a little closer. Okay, cute. Not doing anything.
Maybe it's on too high of a scale. Can you turn that down?
I'm on UHF.
Oh, try
No, I
VHF.
mean, the
Let me,
field
let me-
strength meter probably has different scales, doesn't it? I mean,
No, that one there, this one doesn't. Okay. No, it's not gonna, I'm too long for VHF. Try it now.
it's doing something. It's jumping. I mean,
Is it?
makes it
Yeah,
bump.
it's not much though. No, it's still nothing.
Nothing.
More in. Let's try it even closer. No, it's going to need to be on UHF. Oh, it's digital. It probably is not going to use a nice analog signal.
What's that?
Let me
Oh, he's on digital? Is that the
Yeah,
problem?
yeah.
yeah, I didn't bring my other HT.
That's digital too, isn't it?
Yeah, we should be able to transmit without getting into our computer.
You got an analog? I got an analog, one of the analogs in there. We'll talk about this. There's a couple kinds.
Oh, and I do got simplex. Okay.
There's, let's see if that'll,
Katie found me Joe testing.
typically that will go up to, let me try. Typically I'm going to go right up here as close as I can. See how it deflects the meter? Typically it goes up about full scale at this point. Now watch when I'm vertically polarized. Okay. Watch what happens when I turn. Yeah, I'm too close now. See, it's too close to do that. We'll do this demo later, and I'll bring my VHF radio in here. But this is a field strength meter. This is not a precision instrument. This is a multiple thing that does RF power and SWR and signal generator stuff. This is not a precision instrument. This only measures relative field strength. So one versus another. But you can use a field strength meter to adjust your antennas, adjust your transmitter. You can use it to check your radiation pattern. That's how I want to check my radiation pattern. I can walk around from the back of my beam antenna, the front of my beam antenna, and check the relative. Now, if I got a front to back ratio on that, I should see some kind of relative correlation with that. If I got a calibrated one, I can do RF exposure. I can measure how much RF energy I'm transmitting is in a particular area. We have to do RF exposure evaluation. But that's going to need to be a laboratory grade. If you're going to do that, if you're going to need to do something critical, you're going to need a calibrated laboratory grade device like that. Actually, this one even has a calibration sticker on the front of it. It's been calibrated relative to the National Bureau of Standards. The one I have is simply what most have hams. They're a non-precision thing, and they measure relative measurements. Is what you're really interested in. We talked about dipole antennas, and dipole is half wavelength long, 2 quarter wave sections. What about a vertical antenna? Well, a vertical antenna uses the same principles as a dipole. The difference being, instead of being a half wavelength long, it's only a quarter wavelength long. You're only using 1/2 of that dipole. The ground, or something that looks like the ground, makes up the other half of that antenna, the virtual ground. You can take a quarter wavelength antenna, mount it right there at the ground level, spread some wires out, connect it to the other side of the feed line for ground, and make a vertical antenna. You can also make a multi-band one. Some of these have radials on them. That's the radiating part. That's the ground on the other part, the other half of the antenna. But one of the things about ground mount antennas is the ground reflection losses affect feed point impedance. How good your ground is affects what the actual feed point impedance is down there. So you may need to put a matching section down there. And we'll talk about matching sections in just a little bit.
Is that the same as a counterpoise?
Yep,
Okay.
true enough. It's essentially the same. So if you're using radials for your ground, horizontal radials with a vertical antenna, the feed line impedance is about 35 ohms. So you want about 650 ohms if you can. If you start grouping these things down a little bit, the point impedance starts going up. Here's an antenna. Shows you don't have to buy an antenna. What band do you think that one works on?
That's the one at UHF.
UHF. This is a 70 centimeter antenna. It's about 6.5 inches long. This has a 50 ohm. It's built on a PL259 connector. There's my radials. They're bent down about 45 degrees. That has essentially a 50 ohm impedance on it. If I go all the way down, make it look like a dipole, the impedance goes up to about 72 ohms. And that is what the characteristic impedance of a true dipole is, about 72 ohms. You can take a dipole antenna and you can draw both legs down the dipole antenna, and that'll lower that to what's called an inverted V, and that'll be about a 50 ohm impedance point antenna as well. So it's a function of how far you drop it down. You droop the antenna or drop the radials, raises the impedance. Vertical antennas. I want to operate on, I'll put a vertical antenna up. Now, vertical antenna is what, a quarter wavelength? Vertical antenna is a quarter wavelength. Okay. Half the dipole. I want to operate on 40 meters from my car. Approximately how long does my antenna have to be?
20 meters.
20 meters, yeah. Well, no, it's going to be about 10 meters.
Or quarter wave.
Quarter wave, yeah. Quarter length, 40 meter antenna, quarter wavelength. That's going to be, because a half wavelength is 20. It's going to be about 10 meters. 10 meters is about how tall?
30 feet.
About 33 feet. Okay. What's the minimum height of an overpass on the interstate highway?
It's a lot less than that.
14 feet, 12 inches. So my first overpass, I'm going to clean that antenna off. I'm actually probably going to wrap it over the top of the... Worse than that, how far off the road do you think that when you cross underneath power lines, how far above the road do you think those power lines are? You think they're 33 feet above there? Those power lines typically aren't run at 110. Those are usually about 440 volts, because that's where the transformer is behind your house. So you're going to be right along, you're going to impress 440 volts right on your antenna. Plus the fact it's totally unmanageable. You know, how do you keep it straight up in the air? Well, what do you do? Well, how about a 40 meter antenna like that? That's 8 feet long. That'll work. Put that in the bumper of my van. I can drive it in here without hitting the ceiling. I can't make it through the door, but I can drive around here without hitting the ceiling. That's 8 feet long. That's a 40 meter antenna. Didn't we say that to be a quarter wavelength long, it had to be 50 ohms a bit, had to be a quarter wavelength long? Well, there's a way around that. This piece of the antenna here is metal. This piece here is fiberglass. What do you see on that fiberglass? You see, looks like a piece of wire wound around that. It winds up here for a while, and then all of a sudden it winds real close together, and then it winds back out here again. Think of it real simply. I got about 4 feet here. Okay. How much more antenna length do I need to get to be 33 feet? I need about 29 more feet, right? I got probably about 29 feet of wire around this thing here, give or take. Actually, what this does is that as you shorten an antenna, it becomes highly capacitive. Remember we talked about impedance was capacitive, inductance, and pure resistance. Impedance, a shortened antenna becomes highly capacitive. I can offset that by putting an inductor in it. So I've got part of this antenna here part of this makes up for the rest of the length. This coil run real close together here, that fat spot's a coil, because you can't see it because the wires are run right. You can't hardly feel it because of the coating on it. That's a coil, okay. Okay, and then that is some more to make up for the rest of the antenna. Think of it that way. Got pretty much a center-loaded antenna. I've lengthened the antenna with a little bit of wire, and I've compensated for the high capacitive by offsetting it with a suitable inductance, so that I get essentially about 50 ohms. I'm trying to get 50 ohms down here. That's not bad. Well, why would anybody want to use a full wavelength antenna? Well, these aren't very efficient. Again, there's no free lunch. These things this thing probably only has about about maybe 35% radiation efficiency. So if I put 100 watts into this thing, I'll be lucky to get 35 watts actually out of the antenna. But it's that or nothing. Still, that's not bad. You can communicate quite well on 40 meters on 35 watts. Where's my ground? What becomes my other half of my antenna? The vehicle. The metal body of my vehicle becomes the other half of the antenna. So mobile antennas are practical. They come in a lot of shapes and sizes. They come in ones that have coils like you see here. They come in antennas that have open coils. That coil you saw wrapped around the middle, there's an open coil one. That's a little more efficient because the coil's bigger. Open coils antenna. These have a coil inside of this horizontal piece where you can slide it up and down and short turns of the coil out to change the coil inductance. That's called a screwdriver antenna, so you can work multiple bands on that. Vertical antennas are nice, but what you suffer efficiency is what you suffer. You give up efficiency. So 8 feet is about the maximum practical length. They require inductive loading coils and sometimes capacitors to compensate for the short length. They have very low radiation or low radiation efficiency. The higher you get with 8 foot as a given length, the higher you get in frequency, the closer you get to 8 feet being a quarter wave radiator, the higher the efficiency becomes. These are pretty good on 10 meters, but they're not very good at all on 80 meters. But still, they're better than nothing. I won't go into my long-range story about traveling with a 3-foot high, 20-meter antenna traveling up to the Midwest, which was really a compromised antenna, and I did remarkably well on it, considering. So it was the best it was either not talking or talking, and I did quite well on it. Didn't do much international stuff, but I did a lot around the U.S. There's an interaction with the vehicle body. You may have to tweak and adjust the antenna based on where it is on the van, on your van or your truck or your vehicle, about where it's located. You may have to adjust it to get the impedance, but it does have an interaction with that. It has a very narrow bandwidth below 2:1 SWR. That's what you want to make sure is that you may get it tweaked down so you've got a real nice standing wave ratio at one frequency, but you move off that frequency and the standing wave ratio goes up quite a bit. And of course, most of your radios don't like to operate more than about 2.5 to 3 SWR before they start powering down on you. So, and there's no such thing as a free lunch. You're trading off efficiency. You're trading off for a dipole antenna. Dipole antenna is a good all-around antenna. We'll go through our review. How can you avoid a ground loop? Remember what a ground loop was? Connect all grounds in series. Connect an AC neutral conductor to the ground wire. Connect it to your socket. Avoid using lock washers and star washers, or connect all ground conductors to a single point. D. Connect them all to a single point. What could be a symptom of a ground loop somewhere in your station? You receive reports of hum on your station's transmitted signal. The SWR reading gets suddenly high. An item in your station starts to draw excessive amounts of current, or you receive reports of harmonic interference from your station.
It's A or D.
If you said A, you're correct. It won't change harmonics. It won't cause your radio to radiate necessarily on different frequencies, but it will distort your signal. You get a lot of hum. In some cases, you might even, if you're touching a microphone or something like a ground, that's grounded, and you touch on the piece of equipment, you might get a little bite, too. Make an RF bite. That's when that one needs to be grounded. How does a signal that reads 20 dB over S9 compare to one that reads S9? 20 is 100 times. 20 dB is 100 times more. 10 dB is 10 times, 20 is 100 times, 30 is 1,000. Remember, it's not linear. 20 dB over S9. S9 is common, you're talking about 20 dB. Remember that little chart we had there that said,
All right, 20 dB, that's 100 times. But,
what happens to the feed point impedance on a ground plane antenna when its radials are changed from horizontal to downward sloping? When we lower the radials, what happens?
it increases.
It increases, decreases, stays the same, reaches the maximum angle, and you said it increases, right? Whoop, wrong one. You're right, it increases. What is near vertical incident skywave propagation? NVIS. Propagation near the maximum usable frequency. Short distance, maximum MF or HF, medium frequency or high frequency propagation using high elevation angles. Long path propagation at sunrise or double hop. High elevation angles, it forces the elevation angle, it forces your radiation pattern up in the air by lowering the antenna. What configuration of loops of a two-element quad antenna must be used for the antenna to operate as a beam antenna, assuming one of the elements is used as a reflector? So they're asking you about the reflector, right? The drill element must be fed with a Ballon transformer. There must be an open circuit in the driven element at the point opposite the feed point. The reflector must be approximately 5% shorter than the drill element, or the reflector must be approximately 5% longer than the drill element. It's got to be longer. Your reflector is always the longer element. What sound is heard from an audio device or telephone is interference from a nearby single sideband phone transmitter? Steady hum whenever you're on the air, on and off, humming or clicking, distorted speech, or clearly audible speech? Distorted speech. Which of the following is a danger from lead tin solder? Can contain food part. Lead can contaminate your food if your hands are not washed clearly after handling it. High voltages can cause tin lead solder to disintegrate suddenly. It can cold flow, causing shorts. Or RF energy can convert the lead into poisonous gas. A, right. Why is it not B?
oh, let's see.
Remember we talked about not soldering your ground wire to your ground, not soldering to your ground rod?
Yeah, to tell you the truth, I wondered about that
Okay.
myself.
What would I tell you about what lightning has high current, right?
Uh-huh.
High voltage doesn't make a difference. It's the current. It's the amount of current that comes through that heats it up. That's why. That's why that one shouldn't trick you, because it said volt. But there's only one word, voltages, not current. Discussion?
All right, so you pass your test today. You buy, a nice little HF kit, have your nice antenna, and then you have a lot of different types of cable different types of cable that you can choose from. When it comes to coax, you don't want to basically buy the cheapest stuff that you can find. Other than your antenna, your coax is going to be the other critical accessory that you're going to have. Right here we show 5 different types. RG59, just under 1/4 inch. RG59 is going to be a 50 ohm cable. That's something that we will use if we have to. RG6 quad shield, RG11. The RG6 and RG6 quad shield are going to be 75 ohm 75 ohm television. The large one down here, the Heliax, that's something that you'll find on repeater installations. It's got a very, very, very low loss, but it's about an inch or even larger than that, and it's very, very expensive. So when it comes to feed lines, the impedance of the feed line is the most important thing that you got to look for. The main type that we use as far as coax is going to be 50 ohm. Television is generally 75 ohm. We also have 300 ohm. This is more for television. I've heard of some hams using it. And then we have a 450 ohm ladder line. That's just basically 2 copper wires separated by a little insulator there. The basic layout of coax, you've got your copper conductor in the very center, surrounded by a dielectric, usually like a foam. The shield, depending on what kind you get, the shield can be just a braid. It may be a braid and a aluminum wrapped, and then the outer jacket for weather protection. Now this is a chart that's going to show you basically the loss for the type of coax. RG174 here, right here, going all the way to some very large cable. A lot of times RG8X, let's just take that as an example, at 400 megahertz, so in the UHF scale. At 100 feet, you can see this is going to have about 7.9 dB of loss at 100 feet. So that's a considerable amount of our energy lost. The larger you go, we're going to start getting up into some heliacs. One of these two up here, you can see this is the stuff that you'll find in the repeaters, the big thick stuff. At 100 feet, 2.9 decibels or 2.6 decibels. So it all depends on the quality, but more importantly, general bigger is better. Now, if you're going to be setting up something, an HF station, if you look at these, 10 megahertz, it's generally a little bit lower than the higher, just because the what's the word I'm looking for? The frequency length, or the
Impedance?
what's the word I'm looking for? Basically the length of the wave is a lot lower. So the same RG8X cable that we had 7.9 at 400 megahertz is going to be 1 decibel. So you can use the thinner stuff at lower frequencies, but the higher you go, the heavier you'll want to go. So this is, what is this? This RG8X.
It's 8X.
Yeah, that's 8X, and then
This here is called Super 8 low loss, but it's essentially the same as RG213. That's RG213 there.
so as you can see, the larger stuff's going to be, yeah. So you don't want to, when it comes to your coax, you don't want to get the cheapest stuff that you can possibly find. And then it's going to give an example. RG11 at 50 megahertz is going to be a 1 decibel, a 1 dB, 1 decibel loss. About 21% loss just in your feed line itself. Some of the common connectors, SMA, you'll find that on a lot of UHF and higher. It's a very, very small connector. I believe you've got them on your on the HTs. The end connectors, those are also UHF and up. You'll find those more on UHF only or repeaters, just because they do a very, very good job of loss reduction. The BNC, surprisingly, you don't see a whole lot of BNC anymore. I think it's being replaced by the SMA, I would imagine just because of size, and because BNCs are, if you're holding on to an HT and it's got a BNC, it's kind of a loose connector. And then the PL259 is the one that we've all seen, usually on the back of mobile radios. You can use those in your vehicle. Yes, it is on the top there. So when an antenna is properly matched, to the transmitter, you'll get the maximum forward power and the maximum RF radiation from the antenna. This is a clean setup right there. 50 ohms out, 50 ohm coax, and 50 ohm antenna. That's a perfect world. If the antenna is mismatched to the transmitter, some power will reflect back. This is where this is whenever you will get the energy reflecting back through the feed line, and the antenna actual radiation amount transmitted will be reduced from the antenna. So that energy that's reflected back will be converted to heat. Not a whole lot of heat unless you're using a lot of power. This is where we get from the technician class, our SWR, standing wave ratio. It's expressed as a ratio of the forward power compared to the reflected power in the antenna system. So you can see this is how we're going to calculate that. You're going to take your larger impedance, 50 ohms, divided by smaller impedance, and that will give you basically SWR is 2 to 1 in this example. Another example, antenna of 200 ohms and a coax of 50 ohms. That's going to calculate to about a 4 to 1 SWR. And as we remember, an SWR of 1 to 1, that's essentially a perfect antenna, and that's what we all strive to achieve. If for some reason we can't adjust the antenna, the impedance on the antenna or coax, we'll use what's called an antenna tuner or matching network. And he has one right here. Basically what this does is the sole purpose of this little device is to trick the radio into thinking that it has a perfect antenna. Now if you're going to transmit and go through an antenna tuner like this, it's not actually changing any of this right here. You're not going to get any more efficiency out of your antenna. It's tricking the transmitter into thinking that it's got a perfect antenna on there. So you're still only going to get, if you're putting 50 watts out and with your antenna you're transmitting 25, with the antenna tuner you're still going to be transmitting 25 watts, but the transmitter itself is going to think that it's the full load is going out.
And what did you gain by doing that?
It will keep your radio from scaling back.
Oh, yeah.
Because a lot of the newer radios, whenever it detects a lot of a higher SWR, a lot of reflected power, it will actually scale itself back.
But the radio doesn't do that. If you have a high enough SWR going back into your radio, it'll burn the final amplifier transistor.
Oh, wow. Now, let's see. So this is the antenna tuner, and that's the guy in black and white on the right there.
Yes.
What's the green thing?
That is an SWR meter.
Okay.
So whenever you start transmitting, if you don't have an antenna tuner, most newer radios have an SWR built in. You'll see it shooting up as you're talking. Mm-hmm. And then if you put one of these in, an antenna tuner in, you will still be able to transmit, but the radio will actually, it will show you, or the SWR meter will look like it's connected to a perfect antenna.
So the antenna tuner does something with the reflected energy, eats it up so that it doesn't get back to the
Essentially.
Where does it go?
Okay, so you've got your radio here,
Yeah.
SWR meter.
Yeah.
It's going to go,
Still becomes heat.
yes,
It's what?
It still becomes heat.
But it's not going back to the
It's
transmitter.
not going back
Correct.
to the transmitter.
So it's heating up the antenna tuner, I guess.
Yeah, the antenna tuner and still the coax is still heating up. That's where the main mismatch is at.
mm-hmm.
It's absorbing the mismatch. So you see you have a set of variable capacitors and an inductor in there, and that allows the change the resonance point.
Mm-hmm.
So what you're seeing is a resonant antenna at the radio end, you got a non-resonant antenna at the other end. And we talked about how you could get resonant
Yeah.
by frequency and a selection of capacitors and reductors. You can achieve resonance. That's what's happening. You're making your antenna resonant at the radio, but still non-resonant at the antenna itself.
This is a silly question, but why would you do that? Why would you set it up where the antenna has?
Well, narrow bandwidth. And say you have an antenna that's like the one I have on the on a car. Has one spot that's got a very narrow bandwidth on it. When you get outside that bandwidth, if you want to change frequency, the SWR goes up. So if you want to operate farther off, outside that bandwidth, you would put the antenna tuner in there so that your radio can still handle it. Does that make sense?
So,
Okay.
Here's another example. At my house, I have an antenna. It's a big wire antenna that goes over the house. It is not optimally set up. I know for a fact my impedance at the antenna is off.
It's too low, probably.
Let's see. It is probably too low, thinking about it. The antenna tuner will go in between the radio, the SWR meter, and like I said, it basically tricks the radio. It allows me to use that, but it doesn't allow that extra, that reflected power back to my radio. Doesn't mean that any more energy. It's not improving the efficiency of that antenna at all. It's just it's the magician there that's
Keeps the transmitter
yes
happy.
yes. So
I'm just trying to get this picture right. Are the coax, is it all the same size, or are you purposely putting a larger coax on the antenna?
this is just an example. This could also be 50 ohms coax right there, and then 200 ohm antenna. Because regardless what this is going to also have an effect, and then you'll just have to mess with the dials. There's some automatic tuners that will do everything for you, but just to, let's just pretend that that's also 50 ohms. It's just the antenna that's out of whack, because it could all be 50 ohm and then going into a 200 ohm antenna. Okay. So we're going to go into a little RF safety. If you remember from your technician, RF energy is non-ionizing, meaning it does not alter your cells of your skin. What it does is it causes heat. That's how a microwave works. The human body absorbs RF radiation in different amounts at different frequencies. So between 30 megahertz and 300 megahertz, that's going to be where your body absorbs it the most. It depends on the frequency and strength of the RF radiation at the time of exposure. My personal opinion, they always say between 30 and 300 megahertz. I've always gone 30 megahertz and up, because the higher you go, the more your body will. But for the test purposes, 30 and 300 is going to be that critical range right there. And as we go up in frequency, the more your body's going to absorb. The lower frequency you go, the less it will absorb. And do you remember what part of your body was the most susceptible? Your eyes. Your eyes are very, very susceptible to RF exposure. So when you're talking on your HD, you don't want to hold it up against your face. You want to kind of hold it out a little bit. Going back to the microwave, you will oftentimes see in RF equipment, you're talking about duty cycles. Now, the best way to explain duty cycle is using your microwave. So inside your microwave, you have a magnetron. Basically, it's an RF transmitter. You're ready to cook something, so you put whatever it is in there, and you hit 1 minute, high, go. Well, for 1 minute, that magnetron is transmitting, full power into whatever is in, whatever you have in there. For 1 minute, it's transmitting, however many watts, 1500 watts. It's just transmitting solid. That is called the duty cycle. That's a 100% duty cycle. It's working 100% of the time. Compared to if you put it on 50% power, it doesn't actually lower the power, it just lowers the amount of time that it's actually transmitting. So you're transmitting at full power, then turning off. Full power, turning off. Full power, turning off for that minute. The on-off every half the time. That's considered 50% duty cycle. So that's basically the way we can explain the duty cycle. And that leads us into RF exposure. So you're required to know the radiation levels emitted by your equipment for the safety of your household and your neighbors. Anything that's inside of your household, antennas, your yard, about the RF energy that you're transmitting. You know about that, your neighbors don't. This is called the controlled environment. You have direct control over your domain. And then your neighbors, people running down the road, kids playing on the street, that's the uncontrolled environment. You're required to do a periodic evaluation of your maximum permissible exposure. There's different ways that you can do this. You can perform an RF exposure evaluation using any of the following methods: direct measurement by calibrated instrument, or that's field strength meter that we had out. Mathematical calculation based on OET Bulletin 65. That's, you want to make sure that sticks in your mind. OET Bulletin 65, or computer modeling calculations. The computer modeling is the way that I've done it. There are some websites out there they kind of simplify. You put in the frequency, the amount of power, type of antenna that you have, the distance away that you're from your antenna, and it will run the numbers for you and tell you, okay, here's how close you have to be before you're either too close or you're out of limits, or so I've done that for, I can't even remember which frequency, 10 meters, 20, 40, and 80, I believe are the ones, and I've just got them printed out, stuck on the wall, because nothing has changed since I did that. Now if I put a new antenna up, say I put up a vertical antenna, then I'll want to go back and reevaluate that, and that way it'll tell me, if I have to make sure I stay 10 feet away or 20 feet away or anything like that.
What kind of numbers did you get? I guess, what's your maximum power at your transmitter, and then do you see any risky stuff there, or is it?
On HF, not really.
What's your maximum power on your transmitter?
100 watts.
You've got 100
That's
watts.
That's what I calculated it to be. So I said I've got on 20 meters, 14 megahertz, 14. I think I did 14250. I said I was going into a dipole antenna because that's the type of antenna I was. 100 watts, dipole antenna. Where I was, let's see, how far away from the antenna I would be.
And what kind of numbers did you get? How far away?
Basically, as long as I was 3 feet away from the antenna.
The neighbors aren't at any risk at all.
No.
But it's a different calculation for the neighbors. You do a controlled environment calculation for you. You do an uncontrolled environment calculation for your neighbors. So, and what it amounts to is that the time span is different on how much exposure they will have.
They can, I don't know. Go ahead.
Yeah, it gives you the evaluation of 100% duty cycle, which means that tells you that, for example, if I'm going to transmit for an hour constantly, without ever stopping, full 100 watts, I gotta be at least 3.9 feet away. And my neighbors have to be at least 11 feet away, for example. Well, then you figure, I'm okay. But if it said my antenna, if it said I had to be 20 feet away and my antenna was only 15 feet, well, that's still at 100%. So I would need to know that I can't operate 100% of the time.
And when did we
Hey,
Hey,
I know. We won't be doing anything until about 1 o'clock, but we're ready to go.
That's all right, I got out of the doctor's office
Okay.
early, so
That sounds good.
I didn't see anything going on.
so I mean, I can once we finish this, I can show you. I can't remember exactly what the resource. I'd have to look it up, but it's really interesting to see.
Just one more question, and that is, you start seeing dead birds in your backyard? Is that
What's now?
once in a while?
West Nile virus.
You don't have any claim to it.
Okay.
Blame it on something else. Any more questions about this? So you can either use the field strength meter, do the calculations based on that OET Bulletin 65, or computer modeling. I chose to do computer modeling, and then stuck them on the wall just in case, the FCC were to show up at my door. That way I could say,
Put it in your logbook.
yep. Factors that affect the resulting RF fields: frequency and power level, antenna height and distance from the antenna to a person. So that was the distance, how far away somebody was going to be, and then the radiation pattern of the antenna. I have a dipole is what I have, so that's got that figure 8. So that's the direction. Any other questions regarding the RF safety before we move on? Then we go into electrical safety. A lot of this is more or less the common sense thing. So gasoline emergency generators, you don't want to fill it while the engine's running. It could spill on there and start a fire. You want to use it in a well-ventilated area. Never use indoors, ever. I mean, that could give you carbon monoxide poisoning. Do not, one of the most important is, do not connect it to a house wiring without your mains being disconnected. Now I can give you an example of why you would want to do that. Before I moved here to Texas, back in Arkansas, we had a major ice storm and knocked power out for 2 weeks. We had access to a large generator, so my dad brought it home. He made a connector that would plug into the generator, but would also plug into a socket in the house. We turned off the mains, that way none of that power goes back out. But that allowed us to turn on the heater every once in a while, just to bring it up to 50 degrees or whatever the temperature was. Turn on our refrigerator for a little bit to kind of help prevent spoilage of the food. So that's why we did that. So you can do this, but you want to make sure that those mains are powered off. That way everything stays inside your house rather than going out to the grid and causing major problems that way. If you can, bond this to a earth ground. At field day, one of the things that we do is we have generators out there. We'll commonly hook the generator for using a jumper cable to a grounding rod. So that just that'll help with any grounding issues. Fuse protection for your station equipment and other appliances. Use the fuse and fuse sizes that are recommended. You don't want to replace a 10 amp fuse with a 20 amp just because something something in the radio keeps causing the 10 amp to pop. You put a 20 amp, it may be okay, but there will be a problem. It could cause a fire. For other circuits, the fuse or breaker size should be appropriate for the wiring. A general rule of thumb: 20 amps for a 12 gauge wire. 12 gauge wire is a pretty heavy wire. 15 amps on a 14 gauge wire. Never ever ever fuse a neutral or ground wire. That's just that basically eliminates if for some reason that fuse pops, now you don't have any sort of ground at all. GFCI, you commonly find these around sinks or areas where you have water. It disconnects the 120 or 240 volt AC line to a device when the current flowing from one or more of the voltage carrying wires flows directly to ground. Basically, if you have one of these near a sink and you spill something and water splashes up in there, and sort of, instead of shorting out, it's going to cut the power completely. It senses a current as small as 4 or 5 milliamps, and it can react as quickly as 1/30th of a second. So it's fast, just long enough to where it doesn't cause damage to whatever it is. So review. Which of these connector types is commonly used at RF service frequencies up to 150 megahertz? Octal, I like that. PL259 plug. Now you often see PL259 and SO239, or excuse me, SO259. The difference between those, one's a plug, one is a socket. That's, as strange as that is, that was one thing that I always confused. I'd call in and ask about an antenna. Now, does it have a PL2? Well, no, it's got an SO259. Plugs and sockets. How does the attenuation of coax cable change as the frequency of the signal it is carrying increases? It is independent of frequency. It increases, it decreases, reaches a maximum of approximately 18 megahertz.
B.
It increases. So the higher your frequency, the higher the attenuation. And what values are RF feed lines losses usually expressed? Decibels per 1,000, ohms per 1,000, ohms per 100 feet, or decibels per 100 feet?
D.
D. Oh, I thought you said B. I was like, okay, let's start this section over. What standing wave ratio will result from the connection of a 50 ohm feed line to a non-reactive load having a 200 ohm impedance? A? 4-to-1. Yep. Which of the following conditions will cause a ground fault circuit interrupter, GFCI, to disconnect the 120 or 240 volt AC line power to a device? Current flowing from one or more of the voltage carrying wires to the neutral wire. Current flowing from one or more of the voltage carrying wires directly to ground. Over voltage on the voltage carrying wires, or all of the choices? B. Current flowing from one or more of the voltage carrying wires directly to ground. What is the radiation pattern of a dipole antenna in free space in the plane of the conductor? It is a figure 8 at right angles to the antenna. It is a figure 8 off both ends of the antenna. It is a circle or has a pair of lobes on one side of the antenna and a single lobe on the other side. A it is. So it look off the side of the antenna. That's your figure 8 right there. What is the primary purpose of antenna traps? To permit multiband operation, to notch spurious frequencies, to provide balanced feed point impedance, or to prevent out-of-band operation? A. To permit multiband operation. What is the characteristics of impedance of flat ribbon TV type twin lead?
D.
D. 300 ohm. That's the thinner stuff that you always see with the older TVs that you saw right there.
Oh, this guy right here.
Yeah. The 450 ohm is about an inch.
Yeah, I was wondering about that.
Yeah, it's about an inch wide. What standing wave ratio will result when connecting a 50 ohm feed line to an antenna that has a purely resistive 300 ohm feed point impedance?
I'll go with 6 to 1.
Oh, yes, yes.
6 to 1, yes. What percentage of power loss would result from a transmission line loss of 1 dB?
You just have to know that one.
See? Yep. Good job. See, y'all know this stuff. How does the feed point impedance of a half-wave dipole antenna change as the antenna is lowered below 1/4 wave above ground? So we're going to lower it down. It's going to increase, decrease.
Decrease. B.
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 Boy.
Steadily decreases.
Well,
That's it. End of session 3. Final review.